Hi everyone. In the first part of this video, we'll go through some examples of using the standard error formula, and then we'll look at a situation in which the formula can be shortened so that the calculations are a little bit simpler. Before we go into those examples, let's review a couple of points about the standard error. The standard error is larger. In other words, the means of the possible samples that could be selected are more spread out and less accurate overall when either the sample size is smaller or the population standard deviation is larger, meaning there's more spread or dispersion between the members of the population that's being sampled. What this is saying is that in either of these two situations, the sample mean is likely to be further away from the population mean, and more error is likely to be expected. This is our first example of using the standard error formula. It says example 3, but this is actually our first example in this video. This example is talking about a person who's using the long method of finding the standard error. This person is calculating the mean height of every possible sample of 10 people that could be selected from a population of 10 people, and the person is calculating the standard deviation of all of the sample means. What this question is asking us is, what answer would this person get if he or she did all of the calculations correctly? And we're not actually going to do this the long way like this person is doing. We're going to use the formula to get the standard error. There's only 3 things that we need to know to use the standard error formula. We have to know the population size, the number of people in the population. We have to know the sample size, and we have to know the population standard deviation. The population has 50 people. The population standard deviation is 4.5, and we want to find the standard error of all possible samples of 10 people that could be selected from this population. We can plug in those 3 pieces of information into the standard error formula. We know that the population size is 50. There's 50 people in the population. We're dealing with all possible samples of 10 people, so the sample size is 10, and the standard deviation of the population is 4.5. Remember, sigma is a symbol for population standard deviation. So we would just use this same formula. We would plug in the population standard deviation of 4.5, the sample size of 10, and the population size of 50. And we would just go through these steps over here. First, we would subtract inside of the fraction. We would subtract 50 by 10, and we would get 40. And we would subtract 50 by 1, and we would get 49. Then we would divide inside of the fraction. We would divide 40 by 49. And the answer would be 0.82. 40 divided by 49 is 0.82. Then we would just take the square root of 0.82 using the square root key. The square root of 0.82 is 0.91. Now we have to deal with this square root right here. We have to take the square root of 10. The square root of 10 is 3.16. Now we just divide this fraction. 4.5 divided by 3.16 is 1.42. And then we just multiply. 1.42 times 0.91 is 1.3 if you round the answer. So that's our standard error. Now let's look at another example of using the standard error formula. This example is also about a person who's using the long method of finding the standard error. The person is going around and calculating the mean height of every possible sample of 10 people that could be selected from the population, and the person is calculating the standard deviation of all of the sample means. We want to know what answer the person is going to get for the standard error once the person is finished with all of these long calculations. We're not going to do it the long way like this person is. We're going to use the standard error formula. And just like in our last example, we just have to know three pieces of information. We have to know the population size, the population standard deviation, and the sample size. So the population has 100 people. The standard deviation of the heights in the population is 4.5. And we want to know the standard error for all possible samples of 10 people. So we can just use this formula again. It looks like the only thing that's changed this time is the population size. Instead of having a population size of 50, we have a population size of 100. So capital N is 100 instead of 50. And it looks like the standard error still comes out to about 1.3. Here's another example. This example is actually the same example we've seen the last two times. The only thing that's changed is the population size. So now the population size is 200. Actually, all three examples we've done so far are the same. The only thing that's changing is the population size. So now we have a population size of 200, a sample size of 10, and a population standard deviation of 4.5. So capital N changes to 200. Looks like the standard error is about the same, but it goes up to 1.4. It just went up a little bit. Now I wanted to discuss this last part of the standard error formula, which is called the finite population correction. It turns out that this part of the formula only has to be used if the population is small. In other words, if the population is pretty large, this part of the formula doesn't have to be used. And the general guideline is that if the population is at least 20 times larger than the sample, then this finite population correction can be dropped off, and you can just use this to get the standard error. If the population is 20 times larger than the sample, then this becomes the standard error formula. And the reason why that part of the formula can be left off is because when the population is 20 times larger than the sample, the FPC comes out to about 1. It's pretty close to 1. And if the FPC equals 1, then it doesn't really do anything to the formula. If you multiply something by 1, you get the same answer. So basically, when the population is at least 20 times bigger than the sample, the FPC is about equal to 1, which means it can be just dropped off of the formula. So when the population is 20 times larger than the sample, we can use this shortened standard error formula, and it'll give us a roughly correct answer. So here's an example in which the population is 20 times larger than the sample. The population has 200 people, and we're talking about all possible samples of 10 people. So we're going to use both formulas, and we're going to see that they give us about the same answer. So in that problem that I just showed you, it said that the population size was 200, the sample size was 10, and the population standard deviation was 4.5. If you use this formula that we've been using all along, with the FPC at the end, your answer comes out to 1.39. If you just use this shortened formula, in which you divide the population standard deviation by the square root of the sample size, little n, the answer comes out to 1.42. So the two answers do come out about the same. The reason why they come out about the same is because the population is 20 times larger than the sample. This answer is technically correct, and this answer is a little bit off. So the point that I'm making is that the shortened formula gives us an answer that's roughly correct, but not perfectly correct. If actually this answer becomes more and more correct when the population size and sample size get further apart. So if the population was 30 times larger than the sample, this would be even more correct. These two numbers would be even closer together. And if the population was 100 times larger than the sample, then this answer would be highly correct, and these two numbers would be pretty much exactly the same. They would only be very slightly different. So let's look at an example in which the population is 100 times larger than the sample. So when the population is 100 times larger than the sample, the long formula gives us 1.41, and the shortened formula gives us 1.42. These two answers are pretty much exactly the same. So like I said, if the population is a lot larger than the sample, then the shortened formula will give you an answer that's highly correct. Not perfectly correct, but highly close to being correct. The reason why these two numbers come out so close is because this last part of the formula, the FPC, comes out to 0.995, which is very close to 1. So since this number is so close to 1, it pretty much doesn't affect the formula. Multiplying 1.42 by this number is basically just like multiplying this number by 1. When you multiply something by 1, you get the same answer. So overall, as the population size and sample size get further apart, the FPC, that last part of the formula, gets closer and closer to 1. And if the population is at least 20 times larger than the sample, you can get a fairly accurate answer by just leaving off the FPC and using the shortened formula. The reason why you can do that is because when the population is 20 times larger than the sample, the FPC is pretty close to 1, which means it can just be dropped off and it won't affect the answer very much. So here's, well, I'll skip over this example. Oh, I think what I was just trying to show you here is that if you wanted to find the standard error for all possible samples of 3 people that could be selected from this population, the long formula and the short formula would give you about the same answer because the population is quite a bit bigger than the sample size. I think it's actually about 24. The population is 24 times larger than the sample, which is why these two answers came out about the same. So at this point, I wanted to move on to looking at some sampling distribution probability questions. We're going to be answering some questions about the probability of sample means. This will be our first example. We're imagining a population that has 4 people, and these are the heights of the 4 people in the population. And we want to know what the probability of randomly selecting 2 people from the population and